And I'm with the red/purple red/blue because I sell purple team. And today I'm going to give a presentation about our filter wash pump control system. Okay, outline. I'm going to give a system background, and then briefly going over the previous work, steady state, operating curve step, frequency response, Bodie plot, root locus, and also go over the proportional only controller, model result, experimental results, then proportional integral controller, model results, and experimental results. Our system is a simulation of a system at sewage treatment plant in Chattanooga. The filter is used to separate out sewage sludge for landfill storage. Wash water is used to clean the filter, and this is a schematic of the whole system. This is a plot diagram of the system, and the input is power level of the pump, which is controlled manually. Output is water flow rate. And every time I look at this, it's just making me laugh because the old Navy chief used to tell me, he said that he'd have a problem. He said, our system is pretty much, he said that the output, he said the amount of input going into the system is equal to the output plus whatever left inside the system. But it meaning cussing word like shit. So he said, basically he said the amount of shit going in the system is equal to the amount of shit going out plus whatever left stuck inside the system. Objectives.
The book?
No, it's not in the book. It's from experience.
Clear.
Probably.
I shouldn't have said that. I shouldn't have said that. Oh.
It's on record now. We got it.
No, somebody's just stuck their head in the door and said something.
Okay.
How many of you know what Hagrid's favorite statement is? Ooh, I shouldn't have said that.
You're already part way there. Yeah, you already.
That's what he said. That's what he said. Oh, I should have said that.
Okay. Carry on. Objective proportional only controller modeling. Predict KC for critical damp response, for decay response, and KC ultimate. Proportional only controller, experimental to observe the response of the system to a set point change, determine the ultimate gain and ultimate period. Tuning controller for critically damp, water decay, and limit of stability. Proportional integral controller modeling. Plot root locus using power integral and power integral time 4 and power integral 4 times small. And KC value for proportional only experiments. Find KC ultimate and ultimate period T. Proportional only control experimental. Use the value of KC and TU and observe the experimental system responses and tune system. And for steady state input and output, the steady state operates first when output stabilizes, and that's the region we're in. And here's the SSOC of the entire range, from mid-range, from low to mid-range, and high. And this is the output, which is start from 20 to 27, and from 27 to 33, from from 33 to 38. And this is the FOP DT step up model, and we just use this slide just to have something. Well, for our system, for our team, we do the step down, but we're using this just to show that it's a step up. And then we're gonna show you guys our step down information. This is the analysis result gain for all the step up and step down for all three ranges. And so far they're pretty close to each other. Same thing with analysis, this for dead time, T0, for all three ranges. Step up and step down. And time constant now. These look pretty close to me. And this is the FOPDT model for the frequency response at frequency of 0.05 hertz. And this is where you get your amplitude ratio and the phase angle, which allow you to do the multiply. And from here, you get the KC. Oh, here it is. Here's the value that we obtained from the boulder plot modeling. Gain decay, which is 0.69 pound per minute per percent. Time constant is 0.52 seconds. Dead time of 0.6. And the visual analysis is 0.68 for gain and 0.47 for tau and 1.6 seconds for the dead time. And this is the root locus plot, and this is where you get all your KC value, ranging from critical to all the way up to ultimate. And once you get those KC value, that's allow you to do the proportional Hartley modeling, which is you have to break it up into 10 different KC values, ranging from the lowest to the highest, and run each of them. So basically you get 10 different graphs. And for example, this graph here is for critical dam, KC 0.12. And this one right here is water decay. And this is where usually it's, this graph here would usually give you the most data on the settling time, the offset, the decay ratio, and of course this is oscillatory. And this one down here is the ultimate. That's when the system never settled down. So it is oscillatory. And this is the proportional Hartley model result with the ultimate starting at KC value of 4.8, damping ratio of 1, and it's oscillatory, and it's never have a settling time. So there's the same thing with offset. Half decay is 3.8, damping ratio is 0.2, and it's monotonic. And the settling time is close to 10 seconds. Offset is at 2 pounds per minute. The water decay is 3.1. The KC value is 3.1. The damping ratio is 0.23. It's monotonic. The settling time is 6.2, and the offset is 2.2.